In this fairly short video, we're going to have a look at enthalpies of solution. So what happens when ionic substances dissolve and why it is that sometimes these processes give out energy and the water seems to get hotter, and why sometimes they get colder or they seem to take in energy and you need to heat them up. So let's have a look at our ionic solid and our water molecule. So our ionic solid is made up of positive and negatively charged ions. And our water molecule, if we remember, oxygen is very electronegative, so is delta minus, and it's a polar molecule, the hydrogens are delta plus. So if we have a look at our water molecule, it's going to attack and be attracted to our ionic solid. So the oxygen end of waters are going to be attracted to the positively charged ions, the cations in our ionic solid. And they're going to start attacking it and forming bonds with it. And ionic bonds start to break, and we get new bonds, ion dipole bonds, formed between the water molecule and the cation. And the other end, the delta plus end of the water molecules, get attracted to the negatively charged ions, and they start to break up and break away. So as we can see, we've got bonds breaking, ionic bonds breaking, and we've got new bonds forming between the water molecules and the ions, and these are called hydrated ions. Now I've kept these diagrams of hydrated ions fairly simple for the purposes of the diagram, but you might actually get up to about 30 water molecules around a single cation or anion. It depends on the size of the ion, and it depends on whether it's 1 plus or 2 plus. Now, if we're going to have a look at what happens when a substance dissolves, we need to think about going from our ionic lattice, our solid, and the enthalpy change involved in going from that to the hydrated ions. So if we think about it, we've got bonds breaking in our solid, and when bonds are breaking, we know that this is an endothermic process. We have to put energy in to break bonds. And from the other stuff we've done earlier in the week, you'll know that breaking 1 mole of ionic lattice is called the lattice enthalpy of dissociation, and this is endothermic. Now on the other side, we've been making lots of bonds between the water molecules, and they're dipoles, they're polar molecules, and these are ion dipole bonds, and making our hydrated ions. Now this is given a special symbol. This is delta HYD, hyd for hydration, H, and this is the enthalpy of hydration. Now, positively charged ions would have one enthalpy of hydration, negatively charged would have a different enthalpy of hydration, and it depends on the size of the ion and whether it's 2 plus, 3 plus. Overall, the whole process going from the ionic solid to the hydrated ions is known as the enthalpy of solution, and this is given the symbol delta H with a sol written in small letters. So now we need to look at how we would actually go about calculating this enthalpy of solution, going from the ionic solid to the hydrated ions. So we've got 1 mole of ionic solid is going to turn into 1 mole of hydrated ions. And to get there, we're going to have this imaginary state where we've got 1 mole of gaseous ions. Now, we know that to go from the ionic solid to the gaseous ions is known as our lattice enthalpy of dissociation, and to go from the gaseous ions to the hydrated ions is our enthalpy of hydration, and we've got our positive enthalpy of hydration and our negative enthalpy of hydration. Now if I take out the diagrams and I replace it with actual substances, and we'll stick with NaCl because it's probably the easiest one to think about to begin with. So we're going to start off with 1 mole of sodium chloride solid. And we want to work out the enthalpy change for turning that into a 1 mole of solution, so 1 decimeter cubed of a 1 molar solution of sodium chloride solution. So 1 mole of sodium ions hydrated and 1 mole of chloride ions hydrated. And to work out that enthalpy change, we need to go to the imaginary state where we've got 1 mole of gaseous sodium ions and 1 mole of gaseous chloride ions. Now, I don't know these numbers off by heart. I get them from the textbook. If you needed the numbers to do the calculation, they would give them to you in the exam. So they might say, calculate this enthalpy of solution. The lattice enthalpy of dissociation for sodium chloride is plus 780 kilojoules per mole. The enthalpy of hydration of sodium ions is minus 390 kilojoules per mole. And the enthalpy of hydration of our negative chloride ions is minus 381 kilojoules per mole. And it would then make sense, using Hess's law, that we don't have to, if we can't take the direct route, we can take the indirect route. What we're going to have to do is add up, because we're going in the same direction of both arrows, we add up all of the numbers. So our 780, take away the 390, take away the 381, and it adds up to plus 9 kilojoules per mole. So we can see that the enthalpy of solution for sodium chloride is a positive value, which means it's endothermic. And you've probably noticed before, if you want sodium chloride to dissolve in water, it helps if you warm the water up a little bit. It's not massively endothermic, you don't notice a big temperature change, but it helps if you warm the water up a little bit. There are other enthalpy cycles you can do, which would come out as being exothermic, so a negative enthalpy change, and that would be substances that when you dissolve them in water actually make the water get hotter. Okay, have a go at the questions that go with this.